January 13. So up to this point in time, we have finished our kind of our graphical addition of vector subunit. And now what we're going to do is we are going to move into how do you do this mathematically? Because at least when you get to add vectors together mathematically, you just need a calculator. Now, are there sketches that are associated with this? Yes, and but you don't always have to show them. I'm gonna ask that you do, because the whole reason we're doing this both ways is so that you can understand that what you did graphically is tied or connected to what you're gonna do mathematically, and so the math that you do really applies to the pictures that you've drawn in this last activity. Now, in order to, one of the things that you need to keep in mind is when you are playing with vectors graphically, you have a set of coordinate axes that you need to think about in your head. That looks like this. So that when you are dealing with vectors, you are worried about how long are they and what angle do they point at. Unfortunately, when we go to say we need to add two vectors together, mathematically, what we call math with addition, subtraction, multiplication, and division, that really doesn't work with this. So if you said, I want to add vector A to vector B, you can't just go and say, well, I'll take the two lengths and add them together, and I'll take the two angles and add them together, and there's my answer. If it were that way, God, it'd be super simple. But it does not work out that way. So when we deal with vectors mathematically, we are still going to have to think of them in terms of a set of coordinate axes like this, but now we're going to go back to our Cartesian coordinate system, where this is going to be the positive x, and this is the negative x, and this is the positive y, and this is the negative y. Now, when you have to think of vectors this way, you need to be able to combine these two, because really you're doing the same thing. And this is where I do have to ask again, how many people have done vectors in their math class? A little. Do you recall the terminology of the I unit vector and the J unit vector? Kind of remember that? That's what this is. I don't know why the hell they decided on I, because if I remember properly, I is really the horizontal and J is the vertical. I'm not going to use that terminology, but hopefully after you see this, if you have any recollection of that, you'll go, oh, that's exactly what we did in that class. So let's take a look at some generic vector, and I am going to do this specifically focusing on the first quadrant, because this is where the connection between these two is going to be the simplest. So let's say I have some vector, let's see, I'll do it here. If I have some generic vector and I'm dealing with it graphically, so I'm going to play with polar coordinates, I express that vector as a magnitude and then an angle. So again, I'm going to restrict myself to the first quadrant because this is where we're going to be able to establish the math most easily. And then hopefully if you remember the rules will apply equally to whatever quadrant our vector points in. So let's say we have some vector and it points here. And so here is our angle and this is our length. Now, again, I'm going to point this out that I am not putting an arrow over this V because that is not what it really represents. This just represents the length or the magnitude of the arrow. So if I'm going to come over here and draw the exact same vector, I think I've done a decent job with that. I can draw exactly the same thing. But over here, when I am dealing with vectors, mathematically, I am treating them as, I can only look at them as horizontal and vertical. Is this horizontal or vertical? This is a key question. What?
Neither.
Okay. Why do you say neither?
Because a horizontal would imply that it's a straight line, and a vertical line would imply it's a straight line up.
Correct. If this was horizontal, it would just be perfectly like this. If it was vertical, it would be perfectly like this. Now, I'm gonna offer up a different interpretation. Does anybody know what the alternative to saying, well, it's neither of them?
It's both.
It's both of them. Because when you think of anything that is not perfectly horizontal or not perfectly vertical, that means it's going, we would say it's going at an angle. But if it's going at an angle, that means some aspect of it is horizontal and some aspect of it is also vertical. Now, if we're in the first quadrant, the nice thing about this is when we talk about, think of this just from a horizontal perspective. Which way does this vector take us? And you can point. Well, if we're only going to restrict ourselves to horizontal, though, you would just point like this. Now, does the entire magnitude take us horizontally? No. But part of this magnitude does take us that way. What about vertically? Part of it takes us upward. So here is where we're going to explode this picture up and show you, well, what the hell do you do with this when you play with vectors mathematically then? Okay? Oh, this is going to be so good. All right. Where are my colors? We're ready to go here. I'm going to go, we'll go blue and orange. When you play with vectors mathematically, you have to, I'm going to use the concept of break this thing down into just a horizontal vector and a vertical vector. Now, when you do that, this is what it's going to look like. We mentioned earlier that this vector is both horizontal and vertical, but the horizontal part of it, I gotta go over just far. The horizontal part of it would take us to the right, and so we could use just a horizontal arrow like that to represent just the part of this vector that takes us to the right. And then another part of this arrow takes us up. Now, what most people will start with is so the blue represents the part of this vector that takes us upward, and the orange one is what takes us to the right. Now, in order to understand where we're going to go from here, this is actually like a little vector addition problem. So what we do to eventually connect with, well, what math are we going to do with this? We're going to take this, and I'm going to really explode this and make it big. Instead of treating this orange and blue one as these two separate things like this, we are going to add them together tip to tail. Which means the orange one would be there, and the blue one would be there. So this is our length. This is our angle. And when you look at this, this orange piece would be referred to as the horizontal component of the vector. All that tells us, if we were to know that number, is how far does this take us horizontally? Because of that, this piece is referred to as V sub x. Guess what the blue piece is called?
Y.
V sub y. Now remember, when somebody gives you a vector, they are going to give you these two pieces of information, which means you will have a number for this v, and you will have a number for this theta. Anybody know where we're going with this? No? Not yet? Okay.
Maybe tangent.
Now, you're headed in the right conceptual direction. We're headed back to trig. Because in order for us to do math, we have to have not the black, we have to have numbers for the orange and the blue. That is where we will now be able to come back to regular math and say, oh, I can use addition, subtraction in order to process things. Remember we said over here, when all you have are lengths and angles, if someone said, add these two vectors together, you can't just take these numbers for different vectors and say, oh, well, you know when you add, it's like taking 2 plus 2 to get 4. You can't just add the magnitudes together and expect to get the right answer. Because this does not take into account that the direction they point at can be different. But when you go to, but you can do that when you play with vectors mathematically. But in order to play with vectors mathematically, you cannot think of them now as this black thing that points at a certain length. You have to, what they'll call it is resolve that vector, which is a fancy word for break it down, into what I refer to as the horizontal piece and the vertical piece, or the X piece and the Y piece. In books, they'll refer to them as components. This is the horizontal component, this is the vertical component. So, if you pretend that you have this black V, the magnitude, and you have this angle, and I say, I want you to figure out what that orange Vx is, can somebody tell me how you would do it? Somebody can come up with this. Bingo. Because what do you have here? I'll emphasize this. Because you have a horizontal and a vertical side, this is a right triangle. So if you say, what side of the triangle is our magnitude from this? What side of the triangle is this?
The hypotenuse.
The hypotenuse. So when you are dealing with vectors in polar coordinates, what they're giving you here in that mathematical presentation is the hypotenuse of a right triangle. And the theta is this angle between, well, I'm going to say it's the angle that you need to use that you're going to do your trig stuff with. So if I were to say, and I can, yeah, I can get rid of this now. Coming over here. If I say we need to find this, and right now if you're going, why the hell do I need to find that? We'll get to that later. We're supposed to find what Vx is. We would look at that and say, well, since it's a right triangle, V is the hypotenuse, Vx is the adjacent side to this angle, and therefore cosine relates those two to each other. We could say cosine of our angle equals our adjacent side over our hypotenuse. So in the end, when I say what I really want to know is what is Vx, and I'm going to do this all in orange now, what's on the other side? And when you are given information about vectors, you're given those two pieces of information. Okay? Now if we go back and say, all right, let's look at this again. What about this one? Okay? We have a similar thing where we still have these two numbers, but now we want the opposite side of this right triangle. So when we talk about the vertical component or the y component of a vector, we have not cosine, but we have sine of our angle equals this thing that we call Vy in that picture over V again. So if we say what we need in order to play with the vector mathematically is Vy, we multiply across by the V and we get V times sine theta. Okay, now I am going to box these two guys in red. Never forget this, okay? So these two equations here and the concept is the critical thing you need to be comfortable with to transition from playing with vectors graphically, which I think people like because they go, oh, I'm looking at pictures. I can see arrows point in different directions. Unfortunately, you can't do math on the numbers when you do that because it just doesn't work. And what you have to do if you want to play with vectors mathematically is you have to realize that that stuff that you pointed at different angles, you can break that into a right triangle. And the thing you need to really remember about this picture is, and I'm going to separate this in green. This thing, I guess I could put this in another color. Do I have another color? Oh, I have red here. This thing in green is exactly the same thing as those two in red. Okay? That you need to become comfortable with. This thing in black, that's graphical vectors, polar coordinates. When you are going to play with vectors mathematically, you need to go back to your traditional horizontal vertical coordinate system, and you need to break that black vector into these two. And once you do, now you can start to do things like, can I just add numbers together like I usually do? And the answer will be yes. Okay? So, now we need to finish up with one other thing. Again, you guys have gotten this down so I can erase this? All right? Does anybody remember me making a reference angle comment at all?
Yeah.
Like, never use your reference angle kind of thing?
Is that not true?
You never want to use that, and that's what we're going to talk about right now. Because at this moment, if you got a first quadrant vector, we got no problem. And let's see, we're doing orange and blue. So, generically speaking, and I'm using this for Vx and this for Vy. In the first quadrant, what sign should the Vx have? This is where I really want you to connect with, because you guys have played with this your entire life. Which way from the origin do we have to move horizontally in order to be in the first quadrant?
Positive.
Positive. So that means if we have a first quadrant vector and you do this sign, this cosine thing to calculate Vx, what sign should come out on it?
Positive.
It should be a positive thing. What about the y component?
Positive.
It should be positive. Let's say you have a second quadrant vector. When you go to do your break it down, what sign would the Vx have?
Negative.
It would have to be negative because in order to go to the second quadrant, horizontally, you have to go to the left. What about Vy? It goes up, so what sign should this have? It should be positive. Third quadrant. When you go to calculate a horizontal component for a third quadrant vector, what sign should it have? It should be negative because you have to go left, and then what would the sign be for the Vy? Also negative. Finally, what will the Vx be for a fourth quadrant vector? Positive. Because from the origin, you have to go right horizontally if you're going to go into the fourth quadrant. But if you're going into the fourth quadrant, what will your Vy be? It will be negative. You guys getting this?
Yeah.
This is like, we learned that back like in algebra. It's like, exactly. So this is not like some, oh my God, I'm going to give you this new... All we're doing is connecting two things here. Now, when you guys do sine and cosine in math, this is where I'm going to... Let's look at a second quadrant vector. So I'm just going to kind of blow one up here. There's our vector. In math, when someone says, well, what's the angle of this thing? Well, it's the second quadrant. That means it's bigger than 90 and less than 180. Now, when you are taught to play with sine and cosine here, if the correct angle from a vector perspective is this one here. But in math, when you are taught to play with sine and cosine, what they end up saying is, well, use the reference angle. And that's where they say, draw an angle here, and then, I'm going to go ahead and do this because it'll be on video, and then use 180 minus theta, and then start to do your sine cosine. Okay? Am I going up?
No, that's fine.
Okay. Never do that. Okay? Now, this is why. Let's make up a number. Somebody give me some angle for that would make sense with this picture for a theta.
123.
Okay. Let's say, I'll put example. (123 degrees). So what does that mean our reference angle will be here? Who can do that in their head? 57. So this will become 57 degrees. So now, I'm breaking it down like I did here. If this is my vector in black, that means my Vx is a vector that I imagine points that way. And my Vy is a vector that points like this. So if I'm doing, and I'll put the right angle here. So if I'm doing this in math, what they will say is, all right, well, if I want to find this here, and remember, we don't have to put a number on this one yet. If I want to find this, we would start by saying, we have the hypotenuse, this is the adjacent side, so we would say cosine, and in this case we would say 57 equals the adjacent side Vx over the hypotenuse, which is just the magnitude of the vector. Let me put the degree sign there. All right. So if I want to solve for Vx, I would take V and I would multiply it by cosine 57 degrees. Who's got the calculator out? Anybody got a calculator out? Give me cosine of 57. And give it like 5 or 6 digits. Who's got it? Nice and loud. Wait. Is that what people are getting? This is going to be awesome. Oh, no, 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 no. Give me... This has to be dealt with. What's the number you gave me? 899? 8 6. One more. 6. Okay. Anybody get a different one? Ah, you got it. We don't do radians. We do degrees. So this is 0.54463. Okay, so one thing to remember, and I'm not putting it up here. You need to be sure your calculator is in degrees when you're doing this, because when we do our graphical presentation of vectors, our angle will be measured in degrees, not radians. And this happens every year, and I laugh when I think, those fancy calculators, they come by default in radians. And usually people don't end up realizing it until they actually do math, and they're like, I'm not getting those same numbers. And then they point out, well, the calculator by default is in radians, so you need to change it to degrees. We talked about why radians are useful though, right? We mentioned the calculus thing. All you people who've done calculus and you know about derivatives and integrals, radians survive the differentiation and integration process. So for example, if you had to do, if an angular measure that you needed to find something out for was 60 degrees, and you put 60 in to the thing that comes out of your differentiation or integration in calculus, you will not get the right answer. But if you express that 60 degrees as pi over 3 and get the decimal value for that, and you put that value into the thing that you process in calculus, you will get the right answer. So radians are the preferred angular measure in calculus because they survive the derivative and the integral processing that you do there. Whereas if you do things in degrees, you always have to remember to convert them into radians before you go there. So for those who haven't had calculus, you're like, don't worry about it. Hopefully it'll pop in your head when you get there one day and you'll be like, oh, Mr. Penovich told me that first. Okay. Now, I told you never to use this. So I got to go to a different color now. I'll just go with black. Because in math, they'd say, use the reference angle. I am telling you, you always use the full angle measured all the way around from 0 to 360. Somebody got that one? Okay. But negative. Can somebody tell me why you need to use this one instead of this one when you're doing this thing? This is where I'm saying the picture tells you why. Okay, Reese.
It'll give you the right sign.
It'll give you the right sign on the component. In this picture, when you say, well, I need to rethink this black vector as this horizontal vector and this blue vector being added together. Because this orange vector points left, if you want any hope of getting a right answer, you have to have a negative sign on it. When you are taught to use a reference angle in math, you will never ever get a negative sign on anything because that limits the angle that you do your sine, cosine, or tangent for to being positive between 0 and 90. So you will never get a negative number from that. So when you are doing vectors, because vectors are all about the direction, you cannot afford to say, oh, well, I got the right number, but I got the wrong sign on it. Because then when you start to combine those pieces with others, you're not going to get the right answer. So when you apply the two equations that I told you earlier, that I showed you earlier, the Vx equals V times cosine theta and the Vy equals V times sine theta, you have to use, I almost want to say, you would be stupid not to use the full angular measure. Because when you use the full angular measure as it's given to you in polar coordinates, if your Vx or your Vy needs to be positive or negative, it will automatically come out to be positive or negative. And it irritates me to no end when I have people going, well, I'm going to use a reference angle and then I'll figure out, based on which way it points, whether it's positive or negative. If you miss a problem because of that, I want to crush you. Because that is stupid. Why not just use the damn angle that's going to give you the right sign from the get-go? It's not more sophisticated to say, I'm going to make it harder on myself and have to use my logic to determine whether something's positive or negative, when if you just do it the right way, it'll automatically be positive or negative the way it's supposed to be. Now, some people get uncomfortable with this sometimes because when they go, for example, if you're a third quadrant angle You know, let's say it's 217 degrees. People, I have had people go, can you do cosine or sine of 217 degrees? Because that's like bigger than 180 degrees more. It's like they think sine and cosine can only be inside 180 degrees because we always associate it with triangles. You can have sine and cosine for any angle you want. And there, I know that you guys have been exposed to things like the cosine of theta. Let's see, how would this work? The cosine of theta, the way at least they do it with reference angles, is like the, or how is it? They have these little trigonometric things for you where they say the cosine of theta is equal to like the negative of cosine 180 degrees minus theta. They have all these little things that at least when it comes to vectors, it irritates me. You don't need to remember that. You just need to remember, use the full angle. So here is what your assignment is going to be. And I think we're going to hold off on this until tomorrow. We'll have you do it in class tomorrow because I do want you to do this here with me. And for you really intellectual people, this will irritate the hell out of you the way I'm going to make you do this first time. You have 10 vectors. So we'll start with A. You're going to get a blank piece of paper. You guys already got the master list, but this is what you are going to have to do. A is, I got my list over here. We need to break this into AX and AY. In order to calculate AX, what is my mathematical expression that we're going to do?
A times cosine of theta.
It will be A times cosine theta.
Which is 31.
Now, I am going to go ahead and say this. I would love to make you do this, but then there's one other thing that you would have to do and you'd get even more pissed off at me. So, what we're going to do is we will have you substitute in your values in the appropriate place. So where you said A, what should go there?
4.9.
4.9. And then what would we have?
Cosine 31.
Cosine 31 degrees. And then you are going to calculate that. And this is where I'm going to get super picky again. You're going to get a number. What should go on that number?
Positive.
No, it'll already be positive. Components have units. They are the same units of the overall vector. Okay? Now, I will give you some more, I'll try and remind you of this. Tomorrow, I want you to round your answers to the nearest hundredth here. Okay? Then you have to go and do AY. What is AY going to look? What's the next thing you're going to write?
4.9 times sine of 31.
And then you're going to get your number, round it. And what are you going to put on this number?
Centimeters.
And you're going to do this for all 10 of your vectors. Okay? See, I already got the Now, the part about this that I love more than I think, when you think of doing your vectors graphically, whether or not they are correct is dependent upon how precise you are with your work, mechanically speaking. That's not the case here. When I go to do this calculation, I will get a certain number. If you do not get exactly the same number I do, you are wrong. Okay, so whereas when people say, well, maybe my protractor was off a little bit, or maybe my pencil, I could have had it a little bit more sharpened so the line would have been, not as fat, and I would have got a different number. There are some, I'll call them excuses as to why graphical treatment of vectors it has flaws in it. But the thing that people like about graphical vectors is it's graphic. You see stuff. This is all mental. Okay? Now, I don't know if I'm gonna contemplate one additional thing, but I'm just gonna throw it out there, and then I'll decide whether I'm really. I actually kind of want to make you do this. And again, this is just for practice. I want you to give me a quick little sketch of this next to this problem, which would look like this.
Would we?
Just so that I know in your head you have the right picture of what you are doing here mathematically.
Would we need to use a ruler for that?
No, that's the beautiful part. You just hand draw this one, because this proves to me that you have the right picture in your head for what you're doing mathematically here. So now that I'm thinking about it, I think I'm going to have you throw that in there as well. So that means you'll have to be comfortable with, depending on which quadrant the vector points in, how do you present those components of the vectors. So you guys don't have anything for homework. We're going to work on this tomorrow, and we'll give you class time to do it.
Damn, that was a long one.